Hello. I'm starting this series of YouTube videos to document my work as I go through the series of Landau Lifshitz textbooks. I'm starting problem by problem with mechanics. So let's get right to it. Question 1 is about a coplanar double pendulum, and we are going to calculate the Lagrangian. So I start by setting up the coordinate axes. And I start drawing the two segments of the pendulum. There's a first segment and a second segment that begins at the end of the first. And the position of this pendulum can be described based just on these two vertical angles, one for each of the joints. So we have phi1 and phi2. Additionally, each joint has a mass, M1 and M2, and each segment has a length, L1 and L2. Now we're going to write out expressions for each of the coordinates. Our goal is to translate the coordinates phi1 and phi2 and their time derivatives into the more familiar Cartesian coordinates. So x1, x2, y1, y2, and their time derivatives. Now that we've determined the coordinates, we can write the kinetic energy in terms of the Cartesian coordinates. Using the Cartesian coordinates as a starting point is simple because it always has the same form. We have 1/2 m1 times x1 dot squared plus y1 dot squared, and 1/2 m2 times x2 dot squared plus y2 dot squared. Similarly, the potential energy is just the gravitational potential energy. And because the y-axis is pointing down, we need to add a negative sign in front. So we have negative m1 gy1 minus m2 gy2. Next, we're going to have to rewrite each of these in terms of phi1 and phi2 and their time derivatives. We're going to do that by writing the coordinate transformations between the Cartesian coordinates and the phi coordinates. Now that we have these basic coordinate transformations, our next goal is to determine the time derivatives of each of these equations so that we can substitute expressions in terms of the phi variables in for each of the x1 dot, y1 dot, x2 dot, y2 dot variables. Now we can start plugging these in, and then we'll be able to simplify a little bit. You can see that immediately for this first term, we're going to be able to factor out L1 squared and phi1 dot squared, and the cosine squared of phi1 plus sine squared of phi1 that are left over will combine to just a factor of 1. The second term is more complicated because of cross terms. This next term is easier to simplify as we go. So immediately I'm taking the front terms and the back terms from each of the squared expressions and combining them just like we did for the very first term. What remains are the cross terms. So we have L1, L2, the cosines, phi1 dot phi1, 2, along with negative 2L1, L2 times the sines times phi1 dot phi2 dot. Now using a familiar trigonometric identity, cosine theta cosine phi plus sine theta sine phi equals cosine theta minus phi. We can now simplify those cross terms into a single term. We can also combine the two L1 squared terms in front. So now we only have a 1/2 M1 M2 term and a 1/2 M2 term. And now it's time to work on the potential energy. Just like before, we're taking our expressions for y1 and y2 in terms of the phi variables and plugging it into the potential energy function. And lastly, we can combine the kinetic energy and the potential energy into the Lagrangian just by copying each of our earlier expressions into this final expression. And then we'll be done. The goal of this problem was just to calculate the Lagrangian, not to solve any of the equations of motion, or even to express the equations of motion. The next few problems will also be like this, and then we'll get into some more exciting stuff.